Hello everyone, my name is Massimo Aliotto and I'm a professor at the National University of Singapore. I'm very excited to show the demo of our work, which consists in a light energy harvested sensor node with the unprecedented capability to dynamically adapt to the available harvested or battery power over a very wide range of power speed trade-offs, enabling light harvesting operation down to Moonlight. The testing setup for the proposed multi-sensor platform is shown in this picture. A 180 nanometer test chip is packaged and connected to the testing PXI system through the 4 EHDC-I connectors in the same picture. A LabVIEW test program is developed to interact with the test chip for sensor data readout and MCU programming. And an off-the-shelf solar cell with 4 mm by 4 mm active area is used as an energy harvester. A light source is used to control the light intensity under low light conditions. And the source meter is used to monitor the voltage generated by the solar cell used for energy harvesting. A separate source meter supplies the power needed by the level shifters to drive the I/O interface at the voltage levels that are required by the testing equipment. And finally, a high accuracy light meter measures the light intensity hitting the light harvester. In a typical use case, the system operates under office lighting. In this condition, the harvested power is in the order of 1 microwatt, at which the battery charger and VDD scaling are supported by an inductive converter. In this picture, the light intensity is around 350 luxes. The MCU is executing a program that detects signal events based on thresholding. In other words, the signal coming from one of the available sensors is compared to a threshold, and an event is detected when the threshold is exceeded. In this specific setting, the sensor data coming from the GPIO interface is being monitored. As other capabilities of our platform, the signal can also come from an on-chip light sensor, an on-chip capacitive sensor, for example to detect proximity or gestures, and from off-chip voltage mode sensors whose data acquisition is performed through the on-chip sub-nanowatt interface performing data conversion. More in detail, analog to digital conversion and sensors output are read out as shown by the arrow. The system clock frequency is around 75 kHz at the considered light intensity. Next, we turn off the office light and tune the light source to be approximately 100 lux, corresponding to dark indoor light. In spite of the low illuminance coming from the environment, the MCU, all sensors, and the power management unit continue to function properly. In particular, the MCU clock frequency is reduced to 18 kHz to adapt the system power to the reduced illuminance hitting the harvester. As expected, the output of the on-chip ADC, the capacitive, and the light sensor outputs are correctly read out as shown by this arrow. The DC-DC converterless maximum power point tracking circuitry, MPPT, continues also to operate correctly. This figure shows the charge pump clock that tunes the necessary voltages for MPPT. The clock is running at 58 Hz and sets the solar cell voltage at the correct maximum power point of 0.38 volts, as shown in the source meter measurement. Now, the environment light is pushed towards the very low level of 1 lux, corresponding to Moonlight. The MCU, the sensors, and the power management unit continue to function correctly, although slower, as expected from the drastically lower harvested power. In particular, being the harvested power only 3.1 nanowatts, the system clock frequency is now reduced to 7 Hz. The maximum system power reaches 0.47 milliwatts under battery powered operation, whereas the minimum power is as low as 3.1 nanowatts at 1 lux under pure harvesting. The resulting system power dynamic range is 151,600 X, which is at least 2 orders of magnitude better than prior art. This allows the system to operate continuously even when the luminance is reduced to 1 lux, corresponding to moonlight intensity, under purely harvested operation with a millimeter scale solar cell. In other words, the proposed system is able to operate continuously at any level of harvesting, ranging from direct sunlight down to moonlight, and is hence able to be always on in any practical lighting condition. Accordingly, our demo paves the way to a new generation of energy harvested systems that are always on nearly perpetually, and hence do not miss any physical event, in spite of the highly fluctuating nature of the harvested power. Thank you very much for your attention.